Welcome and thank you all for joining us. We're launching this platform to provide another way to connect with our alumni. We hope to bring you bite sized sessions that highlight interesting news related to our chemical engineering research and education. We plan to have a few of these sessions throughout the year. For those of you who don't know me, I'm Umit Ozkan, and I have been the department chair for the past 5 years. I have been a faculty member in the department a bit longer than that, joining Ohio State in 1985. For the first session, I will give you a quick update on what's happening in the department and then turn it over to what I'm most excited about, which is introducing you to our newest faculty member, Dr. Blaise Kimmel. So a few highlights. This academic year, we graduated 189 BS chemical engineers and awarded 20 doctoral degrees. The faculty size of the department has grown to 31 members, and our research spans into sustainability, many areas related to biofields, including cancer research, advanced polymers, energy, catalysis, reaction engineering, materials, artificial intelligence, machine learning, and many, many more. Our new building, which we moved in 2015, continues to be a showcase on campus, and we're extremely grateful for such a tremendous facility. If you have not had a chance to see the new building, please let me know, and I would love to meet you and give you a tour if you find yourself back on campus sometime. Overall, the department is doing quite well, and we owe a lot of our success to the continued support of our alumni. Our alumni continue to support us in various ways by serving as mentors for our students, by providing capstone design projects, by coming and giving guest lectures in our classes, and of course, by supporting us financially. So to those of you who are here today and who have stayed connected and continue to support us, a huge thank you. Now, I'm most excited to introduce you to Professor Blaise Kimmel. Blaise joined our faculty on January 1st of this year, but he wasn't a stranger, as he earned his BS degree from our department in 2017. He later received his PhD at Northwestern, and then he went on to work as a postdoctoral researcher at Vanderbilt University for 2 years before joining Ohio State. He's affiliated with the James Comprehensive Cancer Center. His research encompasses immunoengineering, synthetic biology, targeted drug delivery, and medicinal chemistry. And we're thrilled to have him as part of our team. And now he will tell you all about his research and his plans for the future. Blaise?
Thank you so very much for that lovely introduction. I really appreciate that. And thank you to all of you for joining us here today. It's an honor to be back here at my alma mater and to now be part of the esteemed faculty here in the department. I'd love to share with you a little bit of background about who I am, the journey that I've taken from being an undergraduate here, and more about what our group is doing today as we bridge the intersection between engineering and medicine. In order to introduce myself a little bit more deeply, I'd love to talk to you about where I came from. I actually come from Florida, but a lot of my family's from here in Columbus, Ohio. I grew up in Melbourne, Florida, right on the beach. And as much as I love Florida, I also have loved Columbus since I was a kid. Being here and coming back to do my undergraduate really meant so much to me when I was leaving high school, and getting to be part of the chemical engineering department was no minimal effort. It's something that I wanted to do since I was a young child, to be in chemical engineering and to study here. What I really loved in my time at Ohio State was I was able to really dive in deeply to see what are the elements that I can do and how can I immerse myself into the culture of the Ohio State community. Some ways that I did that were through undergraduate research here at Ohio State and through teaching. I was very privileged and fortunate to teach 9 different classes as a teaching assistant, but also to be highly involved in undergraduate research. Now, my research was actually in Professor L.S. Phan's lab, where we studied environmental sustainability and I worked in coal-fired directed power plants. But with that, I was able to really dive deep. While it's not the current work that I do today, it taught me quite a bit about catalysis. In that, I was able to present my research at the Denman Forum in both 2016 as a junior and 2017 as a senior, where I will put out an award that I won, where I actually did win second place at the award. Really cool time. Now, from that, I did want to dive a little bit more deeply into research. I found that I really enjoyed it, and I wanted to see how far I could take it. But while maybe environmental sustainability wasn't the right thing for me at the time, I did love the idea of catalysis and wanted to see, could proteins serve a similar function or purpose? To do that, I went off and studied my master's and PhD at Northwestern University, still in the Department of Chemical Engineering. In Northwestern University, I was very fortunate that I was able to study at the intersection of synthetic biology and chemistry. My research, as shown here with some of those colorful images, actually provided some really unique elements to make fluorescent proteins so that we can target and tag cancerous tissue. Now, with this in mind, I was able to do a lot of things in the lab, but I wanted to grow as an individual as well. To grow as a professional, I wanted to see, could I get involved in business and maybe do a business management program? Could I be a better educator and teacher and learn how to do that through a teaching apprenticeship program? And can I actually immerse myself into the culture of another institution, which is also good, but maybe not at the same level in my heart as Ohio State? With that to be said, after finishing my PhD, I went on to do my postdoc research at Vanderbilt University. Moving to Nashville was an incredible time. I loved living there. I loved the music, but I really did enjoy the research collaborations that I got to foster between the College of Engineering and the College of Medicine. My work took on a new, more translational element in that we can make proteins that can not only be useful for targeting cancer cells, but be useful for treating them as well. In order to do that, we did a lot of work in computational modeling to come up with new innovative drug delivery approaches, and we did really unique work that we actually now have in review at Nature Biomedical Engineering. All this to be said, I'm very fortunate and privileged for the training that I've been able to receive. And what I'm really happy to do is now bring all that knowledge back here to Ohio State so that here, my group can grow and foster a new collaborative environment that allows us to bridge the College of Medicine to the College of Engineering. My group joined in January of 2024, but we really actually opened in August of 2023, where we started growing our group, as you see here. We currently have 3 graduate students and have 3 more joining us in the fall, and currently have 4 undergraduates who work with us. We're very excited to be able to go into so many different adventures of cancer immunotherapy and really target rare diseases at the end of the day. I'm very fortunate to have such an amazing, esteemed, and talented group of students who can train with me and really dive deep into cancer immunotherapy. I'd love to show you a little bit more about what we're doing in our group today, both through some slides and then through our lightboard demonstration. The way that we think about research is in the fact that synthetic biology is going to be the promoting interest of our world in 2050. Currently, we're in the silica age, which is a great age. We all have amazing phones and technologies available to us. But what if I told you that those technological devices will be running on peptides, DNA, even proteins by 2050? You'd probably think I'm kind of crazy because why don't they today? Well, our main sectors in synthetic biology are here shown in these 5. And all of them touch every part and facet of life that we all experience daily. The areas that we work in mostly are actually in medicine and pharmaceuticals. And where we make that bridge that I've mentioned a couple of times is in our idea of control theory. Our idea is that we study control theory and process dynamics as chemical engineers in order to maintain equilibrium, steady state dynamics of a system. We want things to stay at an optimal performance control measurement. We want it to be able to generate our process of interest so that we can make products and sell them. We want it to be safe and meet many quality standards that you all in industry tell us how to perfect. But what if I told you that our body's been doing it for millions of years? It's known how to do this, and it can regulate signaling information from other cells in order to make informed decisions. It senses materials and proteins and small molecules from the environment and makes logical decisions at the DNA level so that it can go off using the central dogma in order to go from the DNA to the RNA to the protein and secrete those messages back out. It uses feedback loops, it uses feed-forward loops, cascade control, all the terms and elements that you've heard from control theory. And that's really the dogma of systems biology and immunology. So my philosophy was, if I'm studying proteins and I'm studying cool small molecules and I'm using them to find cancer cells, why can't I teach cancer of something? Why can't I teach immune cells something? And how can I bring the two together in order to study how to better build medicines and pharmaceuticals, but from an engineering mindset and perspective? In order to do that, I'd love to walk through with you a little bit on how I think about designing our research. Our mission that we've mentioned so far to this point has been really rooted into the core principle that we can use antibodies. Now, these are proteins that look kind of like an interesting Y. This antibody that's shown here has two main sections. The first section is right here. These are called the Fab regions. They're able to bind onto pathogens of interest, receptors that they're trying to target, and these might be found on cancerous tissue, bacteria, anything that your body is trying to localize to and deliver its humoral or antibody response to. In addition, we have the FC region. This is a crystallizable fragment that's able to bind onto effector cells, which are also known as immune cells. So in reality, this serves as a bridge between your immune system and its natural cells that exist and the receptors that localize on what it's trying to bind. So in order to make that bridge between the immune cells and your cells of interest, we are thinking about that bridge and how we can engineer it at every step. Now, traditionally, our body makes antibodies. Through the COVID epidemic, we all learned about epidemics of antibody production and how we can try and get a vaccine to make some of these ahead of time. But antibodies are really good for getting to a specific target. Antibodies can also be very good at delivering something with it. One thing that would be great to deliver would actually be a drug. So we do a lot of small molecule design. We think a lot about small molecules and how these could be very useful as immunomodulating drugs. So immunomodulation, what does that mean? That means that we want to either increase or decrease the immune response from your cells. That means that if you have immune cells that should be active and need to be active to get rid of something like a pathogen, we need to think about drugs that will stimulate or excite your immune system and say, please find this and destroy it. Alternatively, some of us might have autoimmune diseases, meaning that our immune systems are a bit too active and they're not able to recognize what's you versus what's a disease. In that case, we need to think about how to suppress or turn down the immune system just to make sure that it's not too hot. We can use this kind of idea as a way of balancing or building our equilibrium design of interest. Now, for those of you who took control theory with me this year, as I do teach control theory, or have taken it in the past, we're always trying to think about how to maintain this brilliant level of equilibrium. And if our system is too high or too low, what kind of regulatory responses can we do as controllers to bring it back down or to increase it in order to maintain that steady state? As I mentioned a little bit ago, our bodies do that naturally. We have feedback to recognize if there's too little or too much of something, and your body makes a logical decision on how to perform. So immunomodulators just act as external types of drugs that we can deliver that can help to teach your body how to do that or to go back to steady state. I'm sure most of us have taken ibuprofen or Tylenol at this point. Those act as the ability to stimulate or suppress your immune system, those inflammatory-based drugs, because in reality, inflammation is the immune response. So those types of inflammatory signaling is something that your body is naturally out of whack on, and you need to bring a drug in order to help to solve that. And now those drugs are great because really it's all about the fact that your immune system is a bit too hot everywhere. So you want to decrease your inflammation. But what if I told you that cancer is very good at evading immunity? Cancer and a lot of diseases are quite good at evading it. They're smart. They've evolved to say, I am a normal, healthy cell. And in addition, I know how to avoid the immune system. I can trick your immune system actually into thinking I'm an organ that needs to grow and that I should be here. It's kind of tricky how to solve cancer problems then, right? Because how do you get this drug into your body to teach your immune system if your immune system sees the cancer cells as self and not as a pathogen. Additionally, how do we make an antibody that's able to bind to those cancerous cells and have any function to bridge this gap between your immune cells and your cells of interest if that's the case? That is the area of intersection at which we work. We need to think about how to bridge these two together and make antibodies that are decorated very effectively with our drug of interest. We need to have the drug on there where this drug is the immunomodulator. So we can get to the cancer cells by binding at the Fab region and deliver this immune modulator so that we can turn a cold tumor, which means it's immunosuppressive or good at evading the immune system, into a hot tumor, one that's filled with immune cells that are actually activating and turning back and reprogramming the tumor cell so that your body no longer sees it as an organ, but it can see it as cancer. We need to think about logical ways in which we can design new antibodies that can target those rapidly evolving and changing tumors. Because tumors are going to keep changing their identity. They have masks. They change their glasses, their clothes, something that makes them look like you and me instead of like a foreign body. We need to think about intelligent responses of binding so that we can only target the cancer cell. Why would that be useful? Well, these immunomodulators are good about turning on or off the immune system when they get into contact with immune cells, but you've got immune cells everywhere. How do we make sure that these immunomodulators only get to the cancerous cell so that we can localize them to target in at cancer without going to healthy cells? We do not want them to go to healthy cells. We don't want them to be over there and be used up. We want to decrease the dosage that we need of our drugs and make sure that we're localizing it here at the cancer cell. To do that, we want to bring it onto this antibody so that it has localized delivery into the cancer cell. And we can make sure that in the delivery process, we're really effectively bringing the drug with it for its attachment and efficacy. What I find really interesting about this is there's so many ways that we can actually engineer this. We are engineers, and while we're not clinicians, we work directly with them to solve the problems that they're facing in the clinic every day. In order to help with translation, we need to think about opportunities for advancement. How can we, as I mentioned before, build better antibodies? Absolutely. How can we make sure that they're targeting new cancer epitopes and mutations and diseases that people are facing every day to make them personalized for you and for me? We also need to think about new immune modulating drugs that we can deliver. We are chemists at heart, as I mentioned with my PhD. So we need to think about ones that are going to be best acting for that type of cancer and actually suppressing or stimulating the immune responses required. Not all cancers want to be for the purpose of inflammatory. Sometimes we want to decrease that inflammation and change how the cancer microenvironment looks. The part that I haven't mentioned that we also think a lot about is this connective piece of the drug to the antibody. A lot of times when people load a drug onto an antibody, they kind of just do it haphazardly. They throw it on, they just hope it sticks, and they're going to deliver it. But unfortunately, what happens in that case when the drug ends up here on the Fab region? The Fab region has no function. It can no longer find cancer cells and bind to them, meaning you lose the whole principle of your delivery. We need to make sure that there's logical decision on where these drugs attach to our antibody so that we can load multiple drugs and improve the delivery yield, but also to make sure that we don't eliminate the functionality of either the drug or of the antibody. In order to engineer this, we think on a systematic approach, our design, build, test, learn cycle. We need to design of what types of cells we'd like to intersect and what kind of drugs we need to activate for the immune system. We need to build it. We need to physically design it and build it out so that we're holding it in our hands, a pure molecule that is homogeneous every time. We need to test it, meaning we do so in vitro with cell culture assays, and we do preclinical assays of our own with animals. Our group is animal facing, so we actually have a vivarium at the Pelotonia Research Center where after building our therapies in the CBEC, we directly go into the PRC, put them into animals, and learn deeply about how we are changing the tumor microenvironment and leading into tumor regression. We need to learn. That's the last step. It's the part that a lot of people leave out, but we need to use AI and machine learning and high dimensional data analysis to actually take all the information we get from the animals and from all of our in vitro modeling, use that data effectively to design the next iteration. Maybe this was good, but could it be better? Can it be reprogrammed or repurposed for a different cancer? And how can we take these approaches forward so that we can deliver new types of immunomodulating drugs, including RNA, DNA, and even peptides, so that we can start focusing on genetic diseases and rare diseases as well? A lot of this is not just theory. I know I'm showing a fun lightboard demonstration of what we do and how we think, but in reality, when someone comes to us and says, this is a real problem that we want to solve in the clinic, we need to not only think about it on the board, but make it a reality for them to hand to a patient. Our research is very translational, and I have appointments and memberships through that so that we can be translational. We do this, we make it work, and we're excited to bring this innovation here at Ohio State so that we can really blossom through the Ohio State Comprehensive Cancer Center and make these therapies a reality, not just in practice, but in Ohio. Thank you for coming and watching with this. We're really excited to have you here today and to continue our discussion. In order to do that, I'm going to show you all a little bit more about where we make these technologies happen at the CBEC and at the Pelotonia Research Center.
The CBEC opened in January 2015, almost 10 years ago, and has been a second home to me since I was an undergraduate student. Leaving OSU, my dream was to one day return back home to Ohio State as a professor. Our building holds 3 main lecture halls, several computer facilities, and laboratory space for all of our faculty. I still remember being the first class of students to take classes here in the CBEC, and to begin my exploration of chemical engineering. My group opened our research lab in fall 2023, and currently we have a group of 3 graduate students and 4 undergraduates. Having the chance to mentor undergraduate students and open exciting new doors for research endeavors is a critical part of the learning experience so that students can apply the engineering principles learned from class directly into practice. Our group is privileged to study the immune system and connect core classes from the chemical engineering curriculum, including process controls, reaction kinetics, and organic chemistry, into the design of new medicine, allowing us to innovate solutions for those with cancer and rare diseases. After building our immune therapies in the CBEC, we can collect crucial preclinical data in our other lab space here at the Pelotonia Research Center. As a professor at Ohio State, I have the opportunity to serve as a bridge between the College of Engineering and the College of Medicine. As a member of the Ohio State University Comprehensive Cancer Center, the Pelotonia Institute for Immuno-Oncology, and the Center for Cancer Engineering, our team gets the chance to design translational medicine and to work at the interface of a highly interdisciplinary research environment of engineers and clinicians. The PRC opened in August 2023 and has several floors available for new faculty to expand their research programs. The animal vivarium, brand new core facilities, and shared equipment allow us to solve problems together, quickly collect crucial data, and learn how our engineered therapies can make an impact on the health and wellness of people within our own communities here in Ohio.
Thank you for taking a tour with us over at the CBEC and the Pelotonia Research Center. It's really great to be here with all of you today and to share a little bit more about what our lab has been up to. Now, in order to do our research, we need to think about where we can make our impact most valuable. And this doesn't just happen in our spaces. It actually happens all over campus through amazing collaborations and through core facilities. Some of the core facilities that we're very privileged to use are because of our membership in the Comprehensive Cancer Center. Specifically, at the Pelotonia Institute for Immuno-Oncology, we have 4 different centers for research excellence shown here, where immune informatics and immune monitoring really is the central piece to all of it. A lot of these core facilities that are available here are really a mouthful, but they're each incredibly useful to all the work that we do in order to study how these preclinical models are going to translate into the clinic itself with people. Now, outside of our collaborative research that's done here at our core facilities, something that we're really excited about is the impact that we can make within our own department. So within our departments of chemical engineering, by the numbers at least, we currently have 31 faculty, and not all of us are actually in medicine or in the areas of biology. We're spread across many different disciplines, and we're really fortunate that 8 of our faculty have won National Science Foundation Career Awards. It's a fellowship that I'll be applying for next summer. Now, with that, we have so many amazing numbers available for who we are. Amazing new National Academy members who were recently elected. We're currently the 21 as our ranking for the undergraduate research program. And we have over $10 million of annual expenditures for our research each year. What's really great though is our graduate program is ranked at #1 in the state of Ohio and 16th among the nation's public institutions and among 27th nationwide. Being in that top 30 is incredibly important because it sets us apart and brings in extremely talented students who would join my group in the groups of all 31 of our faculty members here. Within our undergraduate program, we are equally well ranked. As I mentioned, we're 21st among all schools nationwide, but we're also #1 in the state as well, just as with our graduate. Outside of the numbers within our department, we also want to mention very directly that you can be involved within our department of chemical engineering. Within the chemical engineering departments, you can be involved in many ways. The first of which is that you could be an amazing mentor for our students. We have undergraduate students who are always seeking out mentorship opportunities in which they can learn from you, as you might have been an undergraduate here in our program, a graduate, or a friend and colleague of ours. As a mentor, you can help to lead a capstone project through your company. You can be a mentor for these students directly through one-on-one interactions. You can also come to campus and share your industry experience. I know I myself am always looking for people to come and talk to my controls class about ways in which what we're teaching them does matter for industry. And while I have a couple of friends who work as controls engineers, I'm always searching for more. All of our faculty want you to come back and talk to students about ways in which they can get to where you are today and the things that you need to do or should be thinking about as an undergraduate that will set you apart for your career. Outside of being involved as a mentor, you can also come and assist with your class reunion. We have reunions every single year, and it's up to all of us to come back to campus to enjoy getting to know each other once again. We go off and do amazing things in our careers, but we need to think about coming back home and seeing all the ways in which we're growing as a department, ways in which you can come and get involved, and even be thinking about how you can get back in touch with some of your old classmates. You can definitely contact Sean Gallagher directly if you want to be involved in planning one of these reunions. He's an amazing liaison for the department and is super important for our college for connecting all of us together. Outside of getting involved in those ways, a big one you can do is donations and support for our department. You can help to sponsor students in their research endeavors. You can support our research directly so that we can do new innovative and cutting edge discovery research, and build the technologies that we patent and license and get out into the field. You can also go and create an endowed professorship. I have an endowed professorship under the name of Dr. Umit Ozkan. And I'm really privileged to have that because it helps to extend the power of what we can do. And really, it helped me to bring on a student this fall who I'm really excited to have. It wouldn't have been possible before for me to do that, but through having an endowed professorship, I'm able to continue growing my lab into new spaces where this student is going to be doing computational research, and we're really excited to have him join. In conclusion of your involvements, the 3 main ways we want to stress to you is that you can become a mentor for our students and even our faculty. You can assist with class reunions and help to get back in touch with your old friends and colleagues, and you can donate to support our department so we can continue growing and move up in the rankings and be successful engineers. If you're interested in getting involved in any of these ways, definitely contact Sean Gallagher. As mentioned, here is his email and his phone number. He's available always and would love to hear from all of you. With that, we would all love to hear from you. If you do come to campus, we would love to have you and give you a tour. I myself would be more than delighted to bring you in my lab space and show you all the things that we're learning together and to get you back on campus to see just how much we've grown. We'd love to be able to take some time to learn from each of you and talk with you today. So we do have a portion for live Q&A with me that I would love to connect with you on. With that, if you need to, you can tap onto the Q&A icon in your Zoom window. It should be at the bottom and look just like it does here on our screen for the Q&A button. We have a first question from our panel. It is, What makes you feel valued at Ohio State? And I think this is an amazing question because there's a lot of value that we each feel at our different career stages. Currently, what makes me feel value at Ohio State is getting to talk with students. It's a big reason why I wanted to become a professor and not go into industry is I love teaching. Teaching matters to me because we get to actually instill confidence in our students and getting to show them new techniques, whether it be in the research lab or be in the classroom of how they can actually explore their ideas more deeply is something I really enjoy. So it brings me a lot of value in that I can go in every day knowing that what I do matters and makes a difference for our students and for the people in Ohio who were unfortunately diagnosed with cancer. We have another question that was recently asked. Is your research concentration in the development of ADCs, or is this something different? That is a great question too, because we are advancing a new generation of ADCs. So for our audience, ADCs are antibody drug conjugates, and that is the inspiration behind a lot of what we do. We're thinking of the antibody as our delivery vehicle and the drug as an immunomodulator. Now, traditionally, these ADCs or antibody drug conjugates are where the drug is a chemotherapy, and the chemotherapy's entire job is to kill the cancer cell itself. Our job is actually to teach immune cells. We want to think of cancer cells as little factories and that they can generate the inflammatory signal that then brings in the immune system to come in and attack. We can do this also before you have cancer, and that's a big difference of ADCs. ADCs require you to already have cancer in order for you to then kill the cancer cell. Our goal is that we can localize to different types of cells, which include immune cells, even before you have cancer, so that we can use this as a prophylactic vaccine to teach your immune system more readily how to respond to cancer should you end up getting cancer. We have another question. How long does a PhD student work in your lab? Our students work for 5 years in my lab. Now, I am maybe a bit of an exception in that I do believe that a 5-year PhD is something that can be done very effectively in chemical engineering. I think it takes a lot of grit, it takes a lot of communication between your advisor and your student, and it takes patience. All these are important for you to actually progress forward so that you're not falling into pitfalls that would lead you down a wrong path for a couple of years. You should only have that take about a week or two. You should always be trying and thinking of new ways to innovate and recognize that sometimes there inherently are risks in research. But you should always have those checkpoints built in so that you're making adaptations as necessary and you're growing and developing your program so that you can continue on, complete your aims, publish your papers, and graduate now as a lead investigator of your own. Do you think that the first order plus time delay, or FOPDT model, works well for immunomodulation? I do, actually. I think it works great for immunomodulation. So the first order plus time delay model, essentially in control theory, is that when you're in the Laplace space, which is this magic land that is all about how we think about building down these differential equations, we can actually then break it down into some assumptions of which of these pieces is most important and which of them can be added together just into some time delay kind of term. And that's absolutely true. The reason for that is we have to think about what's the fastest step and the slowest step for anything to be functioning. The same thing is done in a chemical reaction. What's your rate limiting step? That might be based off of concentration of material or time. So when we take in consideration a rate limiting step of time that's used in immunology, meaning maybe there's a specific protein along the way that needs to be expressed in order to secrete that signal, that would then be the dominant time. That would then lead you to then generate a really nice, beautiful model. So yes, as we go into modeling the immune system with our new computational students, it is definitely an element that we will be using. Another question, what is your biggest challenge in communicating with engineering mindsets with the medical community and clinicians? That is an exceptionally great question. Sometimes I get asked by clinicians, you're an engineer, but you don't have an MD, so why are you here? Like, what are you doing in the room? What do you bring to the table? And to say to them, well, we do the design, build, test, learn cycle isn't always an effective strategy. What we need to do is show them that while you can study the biology and learn more about the disease and its prognosis, diagnosis, and treatments progressions, we can build innovative new treatments for you. A lot of clinicians are still using treatments and therapies like ADCs from 20 years ago, 30 years ago. But we can come up with new ones today based on what's currently plaguing our environment here in Ohio. We can make those ourselves in the lab as chemists and biologists, and then use the engineering mindset to optimize our designs. So in communicating to clinicians, the biggest challenge is recognizing that we can optimize and do rapid high throughput screening to make valuable commodity therapies for them that they can actually test. And when we come across that and we bridge in the middle, a recent thing I found is that showing them that we think about immunology and systems biology and how it bridges to chemical engineering for control theory has been extremely effective. We have another question. Are existing immunotherapies along the same line as what your research is expanding? Basically, is immunotherapy different than what you've shared with us today? Immunotherapy is what we're doing. We are absolutely doing immunotherapy. We actually call ourselves immunoengineers. It's a whole new subset of chemical engineers and biomedical engineers. And now our goal is to engineer the immune system. And people do it in many different ways. Now, in making new antibodies, that is in fact a new form of immunotherapy, in that we're trying to target and change the signaling pathways of immune cells. The same thing for making some of these small molecule immunomodulators. So we are doing immunotherapy, absolutely. Another question. It sounds like the main focus of your research is preventative cancer vaccinations. Is there any risk of off-target effects? What are your thoughts on CAR T therapies and monoclonal antibodies as treatments? So in that question, the first part of it is, if we can go back to seeing it one more time, it's a bit long of a question, is you're using your research for preventative cancer vaccinations and if there's any challenge of off-target effects. So if we were to deliver the small molecule immunomodulator on its own, that drug could go anywhere. It would have no ability to localize to one cell or another. And so a lot of people are going, oh no, what do we do about this? How do we decrease the doses required for it? By conjugating it onto the antibody, a strategy that we have is that we can actually localize it to a specific subset of tissue or into the tumor itself. Now, if we're trying to use this as a preventative cancer vaccine, the off-target effects could still be an issue if we're not having a tumor present, but we can localize this to where your immune system lives, like your lymph nodes, your spleens, your thymus. We do actually use combination therapies. So combination therapies are where you can take innovations from CAR T cell therapy. You can take innovations from other existing monoclonal antibodies, and you can use them in combination at different time points. Some of the examples that we've done so far are where we pre-stimulate the immune system with our type of antibody-drug conjugate. We'll call the new innovation, new generation of it. And after pre-stimulating the tumor to reprogram it so that it acts differently and is more immunogenic, meaning that there's more immune cells present, we can then use other existing forms of therapies to finish off our terminal therapy, such as CAR T cell therapy or monoclonal antibodies. The good thing is that in the clinic, you don't need just one. You need to find the one that works best for the patient and is going to be most effective for that person. And while those are all amazing therapies, we can use them in combination, absolutely. A new question. Is chemical engineering the only department working with the Janes? No, actually, there's a lot of colleges, even outside the College of Engineering, that do work with our Comprehensive Cancer Center. These colleges span pretty much every discipline that you can imagine. And within the College of Engineering, a lot of people in the biomedical engineering department, material science engineering department, and even mechanical engineering department are able to help to do this. The last question that we have time for today is, the research center has a lot of room for growth. Are people moving in now? Absolutely. The building has recently opened this academic year. And with that, we have a lot of room available so that we can keep hiring more people to come in. These can be clinicians, they could be engineers, they could be innovators for medicine, and all part of our Center for Cancer Engineering and the Pelotonia Institute for Immuno-Oncology. We have a lot of open room for people to join, and is a big form of our recruitment, both in engineering and medicine. We greatly appreciate all of you for coming today and for being able to take a moment in your evening to share with us a little bit about the questions that you have, see some of the research investments and endeavors that we're doing, and also learn more about ways that you can get involved back in our home department here in chemical engineering. It's an honor and a privilege for me to be back and studying here at Ohio State, now bridging this gap between medicine and engineering. and I'm really excited to see where our department's going to be moving forward with. We really thank you for taking the time to be here today, and always, please come back and visit us. We'd be delighted to have you.